This is Computer Organization and Architecture class. And today we will discuss the second major chapter that is very important in this class, which is about memory. It's entitled Chapter 5, Large and Fast, Exploiting Memory Hierarchy. At the beginning, we will introduce the principle of locality. Programs access a small proportion of their address space at any time. And we have two types of localities, the temporal locality and the spatial locality. The temporal locality means that items accessed recently are likely to be accessed again soon. As you can see here, we access one time, and most likely we'll access another time and another time. We access the same exact location in the memory. So, for example, instructions in a loop or induction variables, you tend to access them again and again. Spatial locality means items near those accessed recently are likely to be accessed soon. So in case of an array, for example, and you access the first member, you will go through an index to the second member and then the third member and so on. So that's an example, the sequential instruction access. And you know that instruction, when we access them, we do that sequentially, one after the other. Also, a data array. By taking advantage of locality, we are introducing the memory hierarchy. There are the main types of storage starts closer to the CPU, or actually part of the CPU. We have the registers, and after that we have the caches. Caches usually are level 1, level 2, level 3, and then we move to the main memory, or as we call it, RAM, for random access memory, and then we have the hard disk, and at the last, after that, we have the tape drive. In terms of size, the tape is very huge, the hard disk is very large, and then the RAM is just large, the cache is smaller, and the CPU registers are very small in size. And in terms of speed, the tape is very slow. It takes seconds to get an access. The hard disk, probably 10 milliseconds. The RAM is 100 nanoseconds. The cache, 10 nanoseconds. And the CPU registers are very fast, probably 1 nanosecond. And cost-wise, the faster the storage, the more expensive it is. So the registers are very expensive. The cache is expensive. The RAM is kind of inexpensive nowadays. The hard disk is very inexpensive, and the tape has the least expensive in terms of cost. So as you can see in this hierarchy, we're trying to gain the advantage of high speed, and that's in the top level of the hierarchy, and also very large size. So we are trying to get the best of both worlds. So we usually store everything on a disk and copy the recently accessed and nearby items from the disk to smaller DRAM memory, or what we call the main memory, and then copy again the more recent accessed and nearby item from the DRAM to a smaller, probably SRAM memory, and from there we copy it to the cache memory, or sometimes we use the SRAM technology to build cache memories And the caches are usually very close to the CPU. You can see in one core, you probably have level 1 cache for the instruction and level 1 cache for the data, and some level 2 caches inside the core itself, and level 3 caches. Sometimes they are close to the core, but still within the chip itself, especially if you are talking multi-cores. Now, the memory hierarchy levels, we have a unit called a block, or also known as a line. This is a unit of copying. Maybe there are multiple of words, and don't forget that when we say words, we mean 32 bits. If access data is present in the upper level, and you can see here in the figure, this is the processor, and we have a certain storage. After that, we have a communication between this storage and the processor, and we also have a communication between that storage and the larger storage. So probably this is a processor, this is the processor, and this is a cache, and here we have the main memory, or a higher or another level of cache. So if access data is presented in the upper level, this means you have a hit. The access is satisfied by the upper level. So the processor tried to look for the information here, and the processor found the information, which means that this is a hit. Now, it's good to define the hit ratio now, which is actually the number of hits divided by the number of access. So the processor will have many accesses. Some of them will be hit, some of them are misses. So among all the accesses, you take the hits and you divide it by the total number of accesses to get the hit ratio. Now, if the access data is absent, it's not there. Now we have a miss. The block is copied from the lower level. Since it's not there, you go find it in the lower level and then copy it into the upper levels. This operation will consume time, and this time is called the miss penalty. And to get the miss ratio, it's actually the misses divided by the number of accesses, or 1 minus the hit ratio that we already get from this formula. Then you access the data supplied from the upper level. So if there is a miss, you copy it, and then the processor accesses the new copy. Now we will talk about the memory technology. We have several technologies. We have the static RAM, or SRAM, the dynamic RAM, the DRAM, and the magnetic disk. The static RAM access time is between 0.5 nanosecond up to 2.5 nanosecond, and it costs from $2,000 to $5,000 per gigabyte. So it's fairly expensive, and the access time is very fast. The dynamic RAM, or the DRAM, the access time from 15 nanosecond to 70 nanosecond, and it costs $20 to $75 per gigabyte. While the magnetic disk, the access time is very slow, 5 millisecond to 20 millisecond, and it's very cheap. It costs between $0.2 to $2 per gigabyte. The ideal memory that we are looking for, it should have the access time of the SRAM, which is very fast, and the capacity and the cost per gigabyte of a disk, or magnetic disk, which is this one. And to be able to get the best of both worlds, as we said, we do the memory hierarchy. Now we will talk about the SRAM and DRAM in a little bit of details. So the SRAM technology, you have actually two inverters back to back, controlled by two switches or NMOSes. They are developed usually in using CMOS technology. And the purpose of those switches is to choose the cell. And you can notice that we are saving the value. If we have 1 here, it will be flipped to 0 and flipped back to 1 to 0 and so on. And this way we are saving the value. And we can either read it to bit line and bit line bar, or write a new value inside. If we have 1 here and 0 here, we write them inside the cell. So it needs 6 to 8 transistors per bit. And the best SRAM, nowadays it has 6 transistors. It's volatile, so it will lose its value when the power is off. Have fixed access time to any bit, and do not need to be refreshed. And because of this, it's considered to be very fast. And the reason that it doesn't need to be refreshed, because it toggles the values between 0 and 1, and this way it saves the value without the need for refreshing any voltages. Thanks to Moore's law, the SRAM are no longer separate IC from the CPU. They are actually built-in cache inside the CPU integrated circuit. If we have multi-core systems and we have the CPU chip, usually we have 4 cores. If we say that we have a quad-core processor, and inside we have the level 1 cache and or level 1 instruction cache, level 1 data cache for core number 1, and similarly for core number 2, core number 3, and core number 4. So it's already integrated and it's built in inside the CPU integrated circuit. Now for the DRAM technology, you are saving the value if it is logic 1 as a voltage in the storage capacitor. So you're storing charges in this capacitor. If the capacitor is full of charges, then you are storing logic 1. If it is empty of charge, then you are storing logic 0. And if you are having logic 1 stored inside, it tends to leak its value with time. And this is why we need to refresh its value every once in a while. So the data stored as a charge in the capacitor. You have a single transistor used to access the charge. So you have the switch, only a single transistor. So basically the DRAM is very small, and this is the reason it's very cheap. Because you have only 1 transistor and a single capacitor. But you must periodically refresh it. The read contents, and when you read the contents actually of the capacitor, you consume its charge. So you need to refresh it when you write back. The charge can be kept for only a few milliseconds. So even if you didn't access it at all, it tends to leak its voltage and you need to refresh it. And it performed well on DRAM row. This is also true for the SRAM. So let's have a look at this module. This module is called Dual Inline Memory Module, DIMM, and it happens to have 2 GB DDR3 technology. And if you look here, you will see that this is rank 1 or side 1. It has 8 small chips, and each one of them is 128 megabyte. It also have another rank in the back. So we have 8 chips in the front in rank 1, or the front rank, and we have another 8 chips that you cannot see it in the slide. It's in the back in rank 2 or in the back rank. So to be able to understand how did we get the 2 gigabyte, we have 128 megabyte chip, and we have 16 chips, 8 of them in the front rank and 8 in the back rank. So if you multiply 128 megabyte times 16, you will have 2 gigabyte, and you can actually get it easily. You know that the gigabyte means 2 to the power of 30, and you know that 2 means 2 to the power of 1. So the total is 2 to the power of 31. And it's broken down as 128 megabyte, which means 2 to the power of 7, that's the 128, times 2 to the power of 20, that's the mega. And you multiply this by 16, and you know that 16 is 2 to the power of 4. So if you add 7, 4, and 20, you will get 2 to the power of 31. So that's 2 gigabyte. DIMM. It's common to call this a RAM or just a memory, and the right name for it is DIMM. Now, if we take this one of the chips, and we zoomed inside it, you notice that we have 8 different banks, from bank 1 to bank 8. Each one of these banks is responsible to generate a single bit as an output. So all of them together will be 16,000 times 1,000 times 8, which means the output is 8 bits, a single bit from each one of them, and this way you generate 8 bits, which means the output is a single byte. Now, the 128 is organized, as you can see, 16,384, and that's 2 to the power of 10 for a kilo, times 2 to the power of 4, which is 2 to the power of 14. That's the 16,384. And the 1,024 is 2 to the power of 10. So if you multiply this one by this one, you will end up with 2 to the power 24, and times this 8, which is 2 to the power of 3, the total is going to be 2 to the power of 27, which is 2 to the power of 7 megabyte, which is the 128 megabyte. It's also broken down here. The 128 is equal to 16 kilo times 1K times 8 banks, which will give you the same number. Now, this bank, if we take one of the banks, let's say that this is bank 1 or bank N, the memory is organized as a memory, or the cells inside the memory are organized as a memory matrix, where you have rows, number of rows, and number of columns. And you need a row decoder to access one of the rows. You know the decoder job is to have one of the line equal to 1 and the rest equal to 0. Similarly, for the column decoder, we'll choose one of the line of the column to be 1 and the rest is equal to 0. And since you are choosing this line to be 1 and this line to be 1, and this is actually based on the input of the decoder, and the input of the decoders of the row and the column is actually the address broken down into two. So for this bank, you have actually 16K, meaning 2 to the power of 14 times 1K, which means 2 to the power of 10. And this means you need, and the single bank will give you 1 bit at the end. So it's times 1, and 1 doesn't make a difference, so we'll leave the 1. So here we have it 2 to the power of 24, and we break it down into 14 and 10. The 10 is actually the address lines that goes here. You have 10 bits, and for the rows, you have the 14 bits. So as you can see, we broke down the 128, we broke down the 24 bits here to 14 and 10 to access a single crossing between the column and the row. In this crossing, you have actually the DRAM that we discussed. So you have a single transistor, and you can see the column coming from here, and the row is coming from here. And actually, the row and column is actually controlling this switch to make the access to the capacitor possible. And once you have the capacitor, you can get the data outside in case you are reading, or write inside the capacitor. Of course, there are other hardwares that helps the reading and writing operations of the memory, like the sense amplifiers. There are also other circuitry that are not drawn in this picture, and you can use input and output buffers to make things go faster when you require to access the memory. So the DRAM performance factors, we have a row buffer, which allows several rows to be read and refreshed in parallel. Synchronous DRAM allows for consecutive access in bursts without needing to send each address by itself, and this improves the bandwidth. The DRAM banking allows simultaneous access to multiple DRAM, and this also improves the bandwidth. This is the one of the performance factors among many. The advanced DRAM organization, the bits in a DRAM are organized as a rectangular array. The best case if we have a square array, and the DRAM accesses an entire row. In the burst mode, you supply successive words from a row with reduced latency. Now, you have heard the DDR RAMs. So we mean by DDR, double data rate RAM. So it's a double data rate. This is the double data rate. That's the abbreviation for it, DRAM. And this means that you are transferring on a rising and falling clock cycle. So when you have a clock, in the rising you transfer, and also in the falling you transfer. And this is why it is double. In the quad data rate, or the QDR DRAM, you have a separate DDR input and another DDR output. And this is what makes it quad, because you have rising and falling for the input and rising and falling for the output. Now, this is a quick look at the cost of the memory from 1980 going down to 2007. And you can see that the capacity is increasing. And at the same time, the cost per gigabyte is decreasing. And this trend, whatever is the type, whether it's red or blue, it's always going down, as you can see, and it goes down exponentially. So in 2007, it's actually really low. It's under $50. And this is also continuing to get lower and lower. The cost is getting lower per gigabyte with the coming years. Now, how to increase the memory bandwidth? And to understand this, look at these three architectures. We have one architecture that is called one word wide memory organization. The other one is wider memory organization, so you can see the width here. And here we have the interleaved memory organization. To understand these, we are assuming one cycle, or we're assuming that we need one cycle to send the address and 15 cycles to access the DRAM, and one cycle to send the word data. And the job for each one of them is requesting forwards, and we will see the difference for each memory. So first, the one word wide memory, which is this one. The miss penalty, what will happen is that you will need one cycle to send the address, and then you need 15 cycles, because you have 4 words that you are requesting to access the DRAM, and the DRAM is actually here. And you need also 4 of a single cycle to send the word data back. So the total is 65 bus cycles. So basically the processor will work with the cache. If it's a hit, good, no worries. But in case it's a miss, now you have the miss penalty, and you have to go to the memory. First, get the address, and then get the or access the DRAM locations, and then get them back. And this is why we have 1 for sending the address, 4 times 15, because you see we have one word wide memory organization. So here we can send only one word. If you are requesting 4, then we have to repeat it 4 times. This is why we are multiplying 4 times 15. And similarly, we are multiplying 4 times 1 for sending the word data back. So this is how we generate the cycles. Now for the 4 word wide memory, the miss penalty in this case, you will have the same one for sending, or the same single cycle for sending the address. And now, since we have a wide memory, we can, if we assume that this wide memory have 4 words wide, is 4 word wide memory, so we can send 4 of them together at the same times, and they will take 15 cycles. Plus 1 cycle to send the word data. So now we have 17 bus cycles. So that's the difference between this one and this one. Here, if we have requesting 4 words, you do them one by one. And this is why you multiply by 4. But here, you get the 4 together in parallel. Let me do it in another way. So you send the first one, and then the second one, and then the third, and then the fourth. But here, you access them in parallel because you have a wide bus. So in total, you need 17 bus cycles. Here we have 65 bus cycles. Now, if you have this organization where there are 4 banks, or it's a 4-bank interleaved memory, as you can see, you have bank 0, 1, 2, and 3. What happens here, you will have 1 cycle to send the address and only 15 cycles to do the 4 words together in parallel, but you still need 4 times a single cycle to send the data or to send the data back from the different packs. So the interleaved memory helps reducing the cost of accessing the DRAM. So instead of if you compare this one to the first one, you don't multiply by 4, as you can see. And this will have 20 bus cycles. Now, if you were asked to calculate the bandwidth for each one of them, what we want to request is 4 words. And we know that 4 words is actually 4 times 4 bytes. So there are 16 bytes. And now we are requesting the 16 bytes, and we divide it by how many bus cycles we have to get the bandwidth. And here we have the bandwidth is really low, 0.25 bytes per cycle. And here we have it 0.94 byte per cycle, and here 0.8 byte per cycle. And you see that this is the best bandwidth, but you are paying in hardware, as you can see. And here it's kind of close, and the hardware is it's not that costly because now the bus is not as wide as the forward wide memory. So this is the way you increase the memory bandwidth by increasing the bus or having an interleaved memory organization. Now, from the memory, we'll talk about the flash storages, and we'll have many SIM cards, as you can see here. And this is a flash that we opened, and this is the inside of the flash. They are non-volatile, so they will keep their value even if the power is off. They are non-volatile semiconductor or semiconductor storage. They are 100 to 1,000 times faster than a disk. They are smaller, having lower power consumption, and kind of robust, but you are paying more dollars per gigabyte. This is if we compare it to the disk and the RAM. Now, there are types of flashes. There is a NOR flash, NAND flash. These are the 2 famous types. So now the NOR flash, the bit cell is like a NOR gate. It has a random read and write access and used for instruction memory in embedded systems usually. The NAND flash, the bit cell is like a NAND gate. It's denser, which is we mean that you have many bits per area, but block at a time access. It's cheaper per gigabyte and used for USB keys and media storage. So if you have a flash memory in your hard, most likely it's a NAND type or a NAND flash. Just to remind you, the NOR gate is this way. This is a NOR gate. And the NAND gate is this way. And we've discussed, if you want to see what is the truth table and what do they mean exactly, you can check your logic design course. Now the flash bits wears out after 1,000 of accesses. So if every time you are plugging your flash in your USB port, access it many times, expect that after a while it will break down or it's no longer works. So this is not suitable for direct RAM or disk replacements, and there is a weird leveling. So what happens, you remap the data to less used block to make the age of the flash better. Now for the disk is also non-volatile, and it is a rotating magnetic storage. If you open a hard drive, you can see that there is a head and there are certain disks. Those disks are actually organized in a cylinder where you have in each one of them a disk, and then in the disk you have tracks and you have sectors. So each track is broken down into sectors. So the disk sectors and axes, each sector records a sector ID, and it's actually a block of data. Usually it's 512 bytes or 4096 bytes. And it has error correction code, or the ECC, which is used to hide the defects and recording errors. So also it has some sort of synchronization fields and gaps. So now we know that the sector is this way, and it's each track is composed of many sectors. Now, to access a certain sector, let's say that we want to access this sector and get the 512 bytes together at one go. So to access a sector, it involves queuing delay if other accesses are pending. So if there are many accesses already in the queue and your request is a new request, so if this is the head of queue and only one empty slot is here, your request will be plugged in here, and you need to wait for 1, 2, 3, 4 accesses to be served before it's your turn. So there is this queuing delay, and there is the seek time, which is the movement of the head indicated by this red arrow. If you are accessing in this sector, the worst case is you are really far from it, so you need to move the head all the way to the right track. And then you have the rotational latency. And if you are trying to access this sector, it's really far away, so you need to circle or half circle until you reach to the head. So you move half a circle until you reach to the head, to that's in the worst case. And after that, once the head is in top of the sector, there is a data transfer delay, and it's indicating by this purple color. And there is also the controller overhead. The controller meaning the hardware controller of the drive, and also some part of it is in software. Now, to understand this, here's an example. Giving a 512 byte sector and 15,000 round per minute, a 4 millisecond average seek time, and 100 megabyte per second transfer rate, 0.2 millisecond controller overhead, and an idle disk. What is the average read time? Since there is no accesses before your current access, we will assume you have a 0 queue time. And you have 4 millisecond seek time that was given to you here. That's the average seek time. And you know that the speed of rotation is 15,000 round per minute. And in the worst case, you need half a cycle to move the sector to the head. So it's half times 1 over 15,000. And this will give you the result in minutes. So you have to multiply it by 60 to generate it into seconds. And the result here is 2 millisecond rotational latency. And since you have 15 or 512 bytes of, or this is the size of every sector, it's 512 bytes, and the transfer rate is 100 megabyte per second, and always be aware, is it megabyte or megabits, the speeds? Sometimes it's written in byte or bits, so be careful. And so we can get the transfer time if we divide the 512 divided by the speed, which is the 100 megabyte per second, and we got the result to be 0.005 millisecond. Notice that these are 512 bytes. 512 bytes. And we add to that the controller overhead, which is the 0.2 millisecond. And the total time, or the total average read time, is 6.2 milliseconds. So we add the 0 with the 4, the 2, the 0.005, and the 0.2 milliseconds. You can see that some of the times doesn't contribute much to the 6.2 millisecond like this one. And some of them actually has a heavy, do the heavy lifting, which is like this one. The seek time takes a lot of time. Also, the rotational time is taking a fairly amount of time. Now, if the actual average seek time is reduced from 4 mega or 4 milliseconds to 1 millisecond, and this is quite the reduction, then the average seek time, if you recalculate, you will find that you are reducing by 50%, from 6.2 millisecond to 3.2 milliseconds. It's about 50%. This point, the disk performance issues, the manufacturer quote average seek time based on all the possible seeks. The locality and the operating system scheduling leads to smaller actual average seek time, and this is good news. Now, the smart disk controller, by the way, and this is the reason that this is not the job of the user, it's the job of the operating system to make sure it's optimizing its algorithms to make it really a smaller actual average seek time. Now, the smart disk controller allocate physical sectors on disk. It presents logical sectors interface to host, like these types, and I'm sure you heard of the SATA. The disk drives include caches, and the reason for the caches is to prefetch sectors in anticipation of access. So if you are actually getting a certain sector, you should prefetch the sectors that are close to it and put it into the cache. So next time you get it from the cache quickly. And this way you avoid the seek and the rotational heal. Now, after this long discussion of different storage devices, we will focus on the cache memory, which is the level of the hierarchy right after the registers. So we have the register first, and right below it, we have the cache. You know, in chapter 4, when we talked about the processor, and in the previous chapters, we use the registers many times. And we know exactly that we have a register, a file, and we can read and write it. Now we will talk about the cache. So the cache memory is the level of the memory hierarchy closest to the CPU. Notice that the registers are actually part of the CPU. Now, given an accesses from x1 all the way to xn, and you have the variables of these accesses randomly put in inside the cache. So before the reference to x of n, you can notice here that you don't have the x of n in the cache. After the reference of x of n, we put x of n inside the cache. This doesn't happen like completely random. You need to answer those or these two questions. How do we know if the data is presented inside? So you want x of n. So how do you know if x of n is here or not? And where do we look? And to answer these questions, here are some introductory examples. And this also defines the first type of cache for us, which is the direct mapped cache, where the location is determined by the address. So now we know that there are addresses of the cache. This is the example here. If we have a cache with 8 locations from 0 in binary to 7, and if we have the memory, which is actually very small memory, but this is just only to understand the idea of the caches. This memory have locations from 0 to 31. So it has 32 locations on. So how the cache and the memory send and receive the data between each other. What happens is, in direct map caches, you have only one choice. And this choice is given by this formula. You have the block memory address, modulo the number of blocks in the cache. So in our example, you know that the number of blocks in the cache is 8. We assume that each location here is saving a certain block. And you have a block memory address based on the addresses that you can see, the numbers right there. So let's take one of them. If we say that we are taking 13, for example. So 13 mod 8 is actually equal to 5, which means the 13 is actually mapped to a single location, as we said here. They'll have only one choice inside the cache, which is here. And there is a competition between the 13 and the 5, the 21 and the 29. And this is obviously because you have a bigger size in the memory and a much smaller size in the cache. So those 4 locations are competing against each other for this location, which means if you access 13, you put it in the cache. Now, in a subsequent access request, you access 29, so you have to overwrite what was inside the cache. Now, to answer our questions, how do we know if the data is presented? And where do we look? You have the cache number of blocks, which is a power of 2. So we have here 8, and because we have 8, we can get exactly where is the place of the data, or where do we look. And we use the low order address bits. So you can see that we can, instead of calculating, I gave you this example, 13 mod 8, and we get the result to be equal to B, or equal to 5. You can do it in binary in a really easy way, because we know that 13 is 10110. So what happens is, we know that the cache is 8 blocks and you need only 3 bits to know the location. So you just take the lowest significant bits, the lowest significant 3 bits, and you know that this will be the location that you should look for in the cache. You can see that it's 5 here, and also here, and also here. Now, to answer the second question, we have tags and valid bits. So basically, to answer how do we know if the data is presented or not in the cache, then we use tags and valid bits to make sure that the data is actually inside the cache. So how do we know which particular block is stored in a cache location? The store block address as well as the data. So that's what we are storing. We store the address and the data. Actually, only we need the higher order bits, and we will call the higher order bits the tag. Which means, going back here, you can see that we took the lower order bits, or the least significant bits, to know the location. Now, the remaining 2 bits is actually a tag. It's like the tag that the ID is coming from close. You have a tag in close to know exactly what's the size of the clause and where is or what's the factory that makes it, and where is it made from, and things like this. Here we have the tags to distinguish between those 4 locations. And you can see that this is 0, 0, this is 1, 0, and this one is 0, 1, and this one is 1, 1. So as long as you know the cache size, you can know that you need 3 bits, and the remaining will be the tags. So now inside the location, you will store the data, not only the data, also you will store with it the tag. So this way, if the processor is accessing the cache and it's accessing, let's say, this address, it will look for the 101 inside. And then look at the tag. If the tag is also 00, and you should save the tag somewhere in the cache, then you know that you are accessing the right information. So that's the first piece of information, which is the tag. The other piece of information is the valid bit. And this is, or we use the valid bit to answer this question. What if there is no data in the location? If there is no data, we will make the valid bit 0. If there is a data, we make the valid bit equal to 1, which means that the data is present. If it's not, then it is not present. And initially, when you just power on the device, all the valid bits in the cache are equal to 0, which means that there is nothing in the cache and it's empty. Now, to understand this better, we have an example. This example is the same, the one that we just explained. You have a cache with 8 blocks. Now we specify that these 8 blocks, each one of them have 1 word per each block. Remember, 1 word is 4 bytes or 32 bits. And we use the direct math. So in the initial state, what happens in each of the locations, the 7 locations or the 8 locations from 0 to 7, now you have a valid bit, and initially they are all 0 or n, so there is nothing present in the cache, and the tag that we need to store, and the data. So next, you were asked, or the next cache or the next axis has the address or has the word address 22. What you should do is get the binary of the number or get the binary of the address. The binary is 01101. So you know the cache has 8 different locations, and you know that you need 3 because 8 is 2 to the power of 3. So you need 3 bits from the binary address, and specifically the least significant 3 bits to know the location. And now, since we have 22, we have 011, this is the right location to save the data. Now you get the data, which is the contents of the address 01101, and we write it down this way, mem, and between brackets, we put the address, and this is the data. The data is, as we specified in the beginning, it has one word per block, which means you have here 32 bits inside the data. So here we have 32 bits. Now, the remaining parts of the address and distinguish between the data and the address. They are different than each other. So the data, you put the 32 bits inside. Now the address, you took 3 bits to know the location, and the other 2 is actually the tag, and you store it inside the cache in the same location. Now, since you just started, of course, it was a mess. There is nothing there, and we put it inside. And we just hear that we just say here that the cache block is the 011. Now, after that, you have another access, which is the word address 26 in binary 01011. So you know the location is here in purple, and you know the tag is 11, and you switch the valid from N to Y, meaning yes, there is a presented value. Similarly here, and you put the data memory of this address. So now you know the drill. You go back again, and next time you have the access of the word address 22. Luckily, we already have it in the cache. So when you write the binary address, you find 011. This is 011. Oh, there is something. Let's check if it's the same thing that I want. So I check the tag with the tag. Yes, it is the same tag, so it's a hit. Similarly, for the 26, I check the location, and the hardware do this job exactly. It checks the location first, and then check the tags. If the valid bit is also equal to 1, or yes, it's presented, then you know that you have a hit. You have a hit, and you can get the data. I said every time that we access, which means that either we are reading or writing this data. Now, more, we have the word address 16, and it's 00001, which will be stored here, and you will find there was nothing there. So now you flip the valid to Y or yes, and then you put the tag right there and the memory content, and it was a miss. Similarly, for the 3, it was also a miss, and we store it right here along with its tag, and we change the valid. The 16, again, we access it, and you know that this is a hit because you will go for this one, you will go and check the 16, and the 16 is actually in 000 right here, and you compare the tags, and you know it's a hit because also the valid is equal to 1. More, we have the word address 18, which is 01001. So it will be in this location and 010. And you notice that previously there was something there. There was this. So if we focus on this location and go to the next slide. So this location have this word address as well. So you go there, and you also find the valid is equal to Y. If you compare between this one and this one, the valid is Y. However, the tag is 11 in the old value, and what you are requesting has a different tag. So what happens? It means that you need to take it out and overwrite it, and you get the new data of this address, and you store it here, and then get the tag and put it right there. And so on. So this tells you that sometimes you have the same location, but they have different tags. And this is by comparing slide 27 and slide 28. So as you can see here, we have the tag 11, and here we have the tag 01, and they are different. So we need to replace this data, the old data, we take it out and replace it by this new data, which is the memory content of the new word address. Now, to put everything together, we should know how to do the address subdivision. So if you are given the block size is equal to 4 bytes, meaning 1 word. And if the cache size is 4 kilobyte data, and the memory address is 32-bit wide, from 0 to 31, from 0 to 30, it's the same representation. Then you need to find the group of bits that represent the offset, the group of bits that represent the index, and the group of bits that represents the tag. If you know how to do the address subdivision, the cache memory would be super easy for you. Now, to get the offset, you know that the block size is 4 bytes, and 4 bytes is 2 to the power of 2. And from this 2 in the power, you know that the offset should be 2 bits. So you have 2 bits in the offset, bit 0 and bit 1. Similarly, we put it here, 0 and 1. Now, for the index bits, you know that the cache block is equal to the cache size divided by the block size. Now, the block size, we know it's 4 bytes. And the cache size, it was given to us, which is 4 kilobytes. This one. So 4 kilobytes, which is 2 to the power of 12, divided by 4 bytes, which is 2 to the power of 2, is equal to 2 to the power of 10. And from this 10 in the power, this means that we have the index equal to 10 bits. So you have 10 bits starting from bit 2 to bit 11. Now, since you know the total is 32, and you know the index bit is 10, and the offset is 2, so you take out from the 32, you take out 10, and you take out 2 by subtraction, and you end up with 20 bits in the tag. And to understand what do we mean by the offset bit, the offset and the index and the tag, this figure tells you what is going on. So you have actually from 0 to 1023, which is 1 kilo different entries. We call these entries. So you have 1,000 different entries. Each one of them will have its own valid bit, its own tag, and its own data. Now, how the access happens, how do you know where exactly or which one of these you want to access? You know it by the index bits. And this is why we have 10 bits here, because this is 2 to the power of 10. So to know exactly which one of the 1K here, you need 10 bits to indicate that this is the location that I want. Now, to know if it's a hit or not, what happens? You compare, there are 2 conditions. The first is the valid is equal to 1. The other condition, when you compare the tag that is stored inside the cache, which is going to be 20-bit, with the tag that is coming from the address that you want to access. If they are the same, they are equal, then they will generate 1 for you, and 1 ended with 1 means that it's a hit. Sorry, there is an overlap here, but this means that there is a hit here. And now you have a hit. If it's a hit, you supply the data to the data outputs. The data is going to be 32 bits, since we say that we are saving 1 word at each location. Now, if you were asked the cache size in bits, this implementation, how many bits inside it? So you say that you have 2 to the power of 10 different entries, and each one of them have 1 bit, which is the valid bit, plus 20 bits tag, plus 32 bits data. And if you calculate this, you will find that it's going to be 53 kilo bit. And be careful, it's kilo bits. If you want to get how much in kilobyte, you divide this by 8 to get the result in kilobyte. Now, larger block size. This is another example. If you have 64 blocks from block 00 all the way to block 63, and you have 16 bytes per block. So as you can see, if you count here, you'll find this is 16. Each box here means that this is a single byte. So you have 16 bytes in each block. Or basically, this is 4 words. 4 words is actually 4 times 4 bytes, which is going to be 16 bytes. It's the same thing. Now, the example here, we have 2 examples to know exactly how to find the location of the inside the cache. To what block number does the address 80 maps? So notice that the address is 80, and you have blocks from 00 all the way to 63. So the 80 is not there because the cache is smaller than the memory, and the addresses is actually related to the memory, which is a bigger size. So what block number does the 80 map to? You say that the block address is equal to 80 divided by 60, since we have 16 bytes per block. So the block address, if you divide 80 divided by 16, it's equal to 5. So that's the block address. What is the block number? Is 5 modulo the 64. Because sometimes when you divide, you might get a number that is more than 64. So to locate it to the right position, you take the modulo 64. In this case, it's 5, and 5 modulo 64 is also 5. So you know that this address is actually inside this block. And that's it. If it's inside this block, when you access, you get the whole block in one go. To know exactly where is it, even though it's not that important because you are accessing a block as a unit, if you count starting from the beginning, and you know that the address is 80, you know that here we have 16, and we have 16, so this is 32, and here we have 32, so up to this point we have 64, and 16 more, so 64 plus 16 is equal to 80, starting from 0 all the way to 79. So the next one is going to be 80. But this is not required to know exactly where is it. The only requirement that you need is the red line. Where exactly is the 80 maps to in the cache, which is actually here. Now, here's another example. To what block number does the address 1951 maps? That's a big address because the memory is huge. So you get the block address by dividing this by 16, which is the size of the block. And you know that the block address is 121, and this is not among the 64. So what you do is you take the modulo, 121 modulo 64 is 57, and you know that this block is going to be here in block 57. Notice that this figure here is not depicting everything. We got here from 0 to 7, which is the first 8. And in between, we have so many, and I also have those at the last. It's also good exercise for you for this cache to know how do you do the address subdivision. Now, since we have 16 bytes per block, so this means that we have 2 to the power of 4 bytes per block. And notice that we are taking the block by bytes. So we have 4, and since we have 4, we know that the offset is 4 bits. Now, this is easy. Since we have 64 blocks, I gave you how many blocks exactly. We said that there are 64 blocks. Then we need 2 to the power. 64 blocks is 2 to the power of 6, and we need 6 bits to access these different 64 blocks. So the index here is 6 bits. And the remaining of the 32 bits is 22 bits. So this is the address subdivision. Now, here is some block size consideration. Larger blocks should reduce the miss rate. And this is due to the spatial locality that we said at the beginning of the chapter. But in a fixed size cache, if you have larger blocks, this means that you have fewer of them. And you can see it here. Here, we have larger block compared to this one. And because of this, we have fewer of them. We have only 1, 2, 3, 4, 5, 6, 7, and 8. If we have smaller block size, then we have many blocks. You can see that this is many blocks. So larger blocks makes fewer of them. And this means you will have more competition. There will be more competition in the cache. From the main memory, many of the locations will compete for the same position. And this could increase the miss rate. Also, larger block is having this problem, which is called the dilution. So since there is a large block, most likely it might have this problem, and you have to get the value again and put it in the cache. Now, the larger miss penalty can override the benefits of the reduced miss rate. If you find a way to reduce the miss rate, but at the end of the day, you have a larger miss penalty, then you are not doing anything. You reduce the miss rate, but you increase the miss penalty. So the early restart and critical word first can help here. Now for the cache misses, what happens? And now we will check what happens when the cache hits, what happens with the cache miss in the read and in the write, when you read or write. Now, this table summarizes everything as we go through the slide. So we will check the read and the write of the cache. And what happens if you are trying to read and it was a hit? What happens if you're trying to read and it was a miss? Similarly for the write, what happens when it's a hit, when it's a miss? So on a cache hit of the read, the CPU proceed normally because you find the data and that's it. You go and continue doing the pipelining in the process, in the processor. On a cache miss, you stall the CPU pipeline. You need to stop and wait for the CPU. And usually you stop for a longer number of cycles because now you are accessing the cache, which is slower or much slower than the registers. So you stall the CPU pipeline. you fetch the block from the next level of hierarchy, and usually this is going to be the main memory or the second level of the cache. And you will have two kind of misses. If it is an instruction cache miss, so if you are looking for the next instruction or the BC plus 4, and you couldn't find it, so after you do this, you restart the instruction fetch again. If it is a data cache miss, then after you stall and fetch the block from the next level, you complete the data access. So basically, in summary, if you're trying to read and it was a hit, you proceed normal. If it was a miss, this means that you need to wait for some time. This is called a penalty or memory penalty. Or sometimes they call them miss penalty. Now, what happens when you have a write hit and a write miss? To understand this, here's the processor trying to access the cache. But this time, you want to write into the memory. Now, the thing is, if you write in the memory, you need to make sure whatever you write in the memory is also the same value in the main memory. Anything you write in the cache should be matching what's in the main memory. So, on a data write hit, could just update the block in the cache. So you just update the block here in the cache and that's it. But then the cache and the memory would be inconsistent. So they don't have the same value. And this is why we have the write through method. So in the write through, what we are saying is you also need to update the memory. So if there is an access into the cache and this access is a write and it was a hit in the cache memory, you also need to update the source memory. Instead of saying this long sentence, we just call it, this is a write through. Now, and because of this, because of the write through, the content of the cache memory and the content of the source memory or the main memory is or will be consistent. Now, because of the write through, you are making the writes take longer time because now you are writing in the cache and you also writing in the source memory or the main memory, and we know that the main memory is slow. And to understand this, here is a quick example. If the CPI is equal to 1, and you have only 10% of the instruction that are stores, if they are stores, this means that you are writing into the cache. And let's say that it takes 100 cycles to write into the memory. Then the effective CPI is no longer only 1. It's 1 plus the 10% times 100 cycles, which will be increased by this amount. From 1, you are increasing to 11. And this is a whopping jump. You shouldn't do this and write through. So we need to fix this or find out a solution for the write through. So the solution is you use the write buffer. So you hold the data waiting to be written to memory and don't wait. So whenever you write something in the cache memory, you write through to the source, to the main memory, but you write it into a buffer. Once you write it into the buffer is quick. You go back and continue the processor tasks, and the buffer will slowly write it into the source memory. So the CPU can continue immediately. Only the CPU will stall on write if the write buffer is full. And this is why you need to choose the buffer size wisely. So at this point, if you have a write and a hit, you need to do the write through. There is actually another way, which is called a write back. So you write in the cache memory, It was a hit, so you write in the cache memory, and the cache memory will write into the main memory. How to do this? This is alternative actually to the write-through. On a data write hit, just update the block in the cache. But you need to know which blocks inside the cache are updated by doing what I'm doing. You are making those dirty. To do this, there is a single bit. We already know that there is a valid bit. Now we have another bit called the dirty bit. Whenever I write on a cache location, you make its dirty bit equal to 1. And now, when a dirty block is replaced, you write it back to the memory. And this is why we call it write back. You can use a write buffer to allow replacing a block to the to be read first, and to make it a little bit faster. So in the write hit, you have two methods, either write through or write back. Now what happens in the miss? In the miss, you're actually trying to access the cache, but you couldn't find. First, you want to write. The processor instruction was a store, so you want to write into the cache, and you try to find the address, and it was a miss. So at this point, you need to go to the main menu. But the question is, should you bring the data from the main memory to the cache, and what should you do? So we have what we call write allocation. So you usually either you are allocating or not allocating. So what should happen on a write miss? This is alternative for the write through, and there is alternatives for the write back. Actually, for the write back, you have one method, and that's it. But for the write through, you have two choices or two alternatives. Either you fetch the block, which means that you are allocating. Either you are allocating on the miss, which means that you fetch the block from the main memory and also put it in the cache. Or write around, and this means write on the main memory and don't fetch the block. And the reason for this is the programs often read a whole block before reading it. And this happens, for example, in initialization at the beginning. For a write back, if your method is write back and you are using dirty bits, you must fetch the block. Since you are writing, you fetch the block and make it dirty. So to summarize everything all together, here are the memory requests. And it depends what type of memory request you are having. Is it read or write? Now, if it is read, if it is a hit, then you read no. If it is a miss, then you have a miss penalty. Now on write, if they are hit, if the write memory access is a hit, the first option is write through. The second option is write back. Now, if it is a miss, you still need to do write through or write back. However, if you use a write through, you have two options. Either you allocate, which means that you fetch the block, or you don't allocate. When you don't allocate, we call it write around. If you are using write back, then you must allocate or fetch the block and make it dirty. Now, this is an example at the end. This example is a real case. It's called Intrinsity Fast Math. This is an embedded MIPS processor with 12-stage pipeline. Our pipeline have only 5 stages. This one have 12 stages. And this could happen if you break down, for example, the decode into 4 stages and the other stages into sub-stages, and you can come up with 12 stages. The instruction and data accesses on each cycle, and you have a split cache, which means that you have a separate cache, one for the instruction, another one for the data. And this is to manage the structural hazard, if you remember. Each 16 kilobyte is actually 256 blocks times 16 words per block. So you have 16 kilobytes, that is 256, which is 2 to the power of 8 blocks. And each one of these blocks are 16, or each one of these blocks is 16 words each. 16 words means that you have 2 to the power of 4, which is the 16, times 2 to the power of 2, because they are words. And you know that each word is 4 bytes or 32 bits. So it's 2 to the power of 2. And this will total to you 16 kilobytes, which is this amount. So what we are saying here, that the instruction cache is 16 kilobytes, and the data cache is 16 kilobytes, and it's broken down is to what you see here. You have 2 to the power of 8 blocks, so you have 256 different blocks. Each one of these blocks have inside it 2 to the power of 4 times 2 to the power of 2 bytes, which is actually 16 words per every block. This is how we break it down. Now, for this example, in the D cache or in the data cache, you do write through or you do write back. You have the capability to do both. In SPEC 2000, the miss rate, after we calculated, we know that the instruction cache miss rate is 0.4%, and the data cache miss rate is 11.4%. And you can see that the data cache miss rate is high, very high compared to the instruction cache. And there is actually a reason for this. The instruction cache execution inside it, it happens to be an instruction followed by the next instruction, followed by the next instruction, and so on. So each time you are applying the spatial locality in every access to the instructions, because you access them sequentially. But in the data cache, accessing data is random. It could be anywhere. And because of this, you will have a higher miss rate. So the weighted average between those two miss rates is 3.2%. Now, to see the breakdown of this kind of cache, whether it is instruction cache or data cache, we need to get the address subdivision first. So the address subdivision, we have 2 to the power of 2 and 2 to the power of 4 as the offset. So here we need 2 bits, and this is the 2 bits. And here we need 4 bits. We will call this one, both of them together, we call them offset. But this one specifically, we will call it byte offset. And now these 4 bits, we will call them block offset. Now, since you have 2 to the power of 8 different blocks, then you need 8 bits in the index, as you can see here. And the remaining bits, the remaining 18 bits, are the tags. And as you can see here, to get a hit, first the valid should be 1. So you know that the index will give you the right location inside the cache. You check the valid bit, and you check the tag that is stored inside the cache with the tag that is in the address that you have as the new access address. If they are the same and the valid bit is equal to 1, then it's a hit. And when it is a hit, you give the data into the data output. But since you have 4 bits for the block offset, now we have a multiplexer. You will have 4 selector lines to select among the 16 different words, because we said that here we have 2 to the power of 4, which is 16 words per block. And here we have a block, and inside the block we have 16 different words. To choose one of these words, we need the mux, and the selector of this mux is going to be the 4 bits in the block offset. Now we will go to measuring the cache performance, but this is the subject of the next video.